Welcome to the Explainer. Today, we're tackling a big question. Why does the solid ground right under our feet sometimes shake with, well, just unimaginable force? We're going to break down exactly how earthquakes form, why they happen, and find out which parts of our planet are most at risk.
So, what is actually happening here? I mean, how can solid rock suddenly start acting like water? It all kicks off with this absolutely staggering amount of energy being released in a flash, deep, deep within the Earth's crust. You can think of it in really simple terms. An earthquake is basically the planet letting off some steam. See, the Earth's crust is constantly under a ton of stress. And when that stress builds up and finally hits a breaking point, boom, it releases all that pent-up energy as waves. And that's the shaking we feel. It's the planet's own stress relief system. Now, to really get where this energy is coming from, you need to know two key terms. The shaking doesn't actually start on the surface. Nope. It starts deep underground at a point called the hypocenter. The place you hear about on the news, that's the epicenter. It's the spot on the surface that's directly above the hypocenter. Okay, so that leads us to the biggest question of all. Why does this energy build up in the first place? What's causing all that stress? Well, the answer is in the very structure of our planet's surface. Turns out the Earth's crust isn't one solid piece, like an eggshell. It's actually a giant jigsaw puzzle made of these enormous, rigid pieces we call tectonic plates. And here's the kicker, these plates are not sitting still. They are constantly, slowly on the move. They're drifting, crashing into each other, and sliding past one another. And right where these giant plates meet, the crust is all fractured with cracks, called faults. These faults, they're the front lines. They are the zones where all that immense pressure from the grinding plates gets stored up, sometimes for decades or even for centuries. And depending on how the plates are moving, pulling apart, smashing together, or just sliding sideways, these faults act in different ways. You've got normal faults, which happen when the crust is being stretched. Then there are reverse faults, where it's being compressed. And then you have the famous ones like the San Andreas, which are called strike-slip faults, where the two sides just slide horizontally past each other. But here's the thing. The movement along these faults, it isn't a smooth, continuous grind. If it was, we wouldn't have these huge earthquakes. Instead, it's a process of sticking and then suddenly slipping. And that stick-slip action, that is the key to everything. After that devastating 1906 San Francisco earthquake, a geophysicist named Harry Fielding Reid studied the ground and had this incredible aha moment. He figured out that the quake wasn't the cause of the ground shifting, it was the result of it, and he called his idea the elastic rebound theory. Here's the absolute simplest way to picture this. Imagine you're bending a stick. As you put pressure on it, the stick bends, right? It's storing energy. That's the strain building up in the rock along the fault. You keep bending it and it stores more and more and more energy until, snap, the stick breaks. It releases all that energy in a powerful shock and sound. That snap is the earthquake. The rock, locked by friction, just bends and bends, storing energy until it just can't take it anymore. It finally ruptures, slips, and rebounds, launching all that stored energy outwards. So the fault snaps and this colossal amount of energy is released. But how does that energy get from the hypocenter, maybe miles below the surface, all the way to our cities and homes? Well, it travels in waves. It's just like when you drop a stone into a still pond and you see the ripples spread out. An earthquake's energy radiates out from that hypocenter in the form of seismic waves. These waves travel through the Earth and across its surface, and that's what creates the shaking we feel. Now, these seismic waves aren't all the same. The first ones to show up are the P waves, or primary waves. They're the fastest, and they have this kind of push-pull motion. Right behind them come the S waves, which actually shake the ground up and down. But the waves that cause the most trouble, they arrive last. Those are the surface waves. They're the slowest, but their rolling motion is what causes the most damage to buildings. Measuring an earthquake can be a little confusing. You hear people throw around words like magnitude and intensity, but they mean totally different things. So here's the key difference. Magnitude measures the total energy released right at the source. It's one single number for the whole event. Intensity, on the other hand, describes how much shaking you actually feel, and that changes depending on how close you are to the epicenter. A lot of us probably grow up hearing about the Richter scale, But today, for the really big quakes, scientists rely on the much more accurate moment magnitude scale. It's just a better measurement because it's directly tied to the total energy the quake released. It looks at the size of the fault that ruptured and how much it slipped, so it gives a way more complete picture of the earthquake's true power. All right, so we've covered the why, that's the tectonic plates, and we've covered the how, that's the elastic rebound. So now, let's get to the where. Where on this planet do these things happen most often? Let's start with a number. A huge number, actually. 81%. That is the percentage of the world's largest earthquakes that all happen within one very specific, very active zone. And this is it. This zone is a massive 40,000-kilometer horseshoe-shaped belt that basically traces the edges of the Pacific Ocean. Its official name is the Circum-Pacific Belt, but you almost certainly know it by its much cooler name, the Pacific Ring of Fire.
The Ring of Fire is, by far, the most active seismic zone on the entire planet. But it's not the only one. There's also the Alpine Belt, which is another major hotspot that runs all the way from the Himalayas over to the Mediterranean. And then you have the Mid-Atlantic Ridge, this massive underwater mountain chain where new crust is literally being born. It's another area of really intense seismic activity.
And all this brings us to one last crucial point. We understand the incredible mechanics of tectonic plates. We can map the planet's seismic hotspots with stunning precision. But for all of that knowledge, the one thing science still cannot do is predict exactly when the next big one will hit. And that, right there, remains the ultimate challenge.